everyone. Today we are happy to have Dr. Liu Yu here to give a talk. So let me please mute yourself, guys. Okay. First I will give a brief introduction.
There's some delay.
Okay. Okay. So Dr. Yu is currently a professor in the School of Electrical and Computer and an affiliate professor in the School of Meteorology, University of Oklahoma. He also serves as the director of operations at OU's Advanced Radar Research Center, which we call it ARRC. Okay, so ARRC is arguably the largest academic research center in radar. Dr. Yu received the PhD degree in electrical engineering from the University of Lincoln, Nebraska in 2000. He then worked at the National Center for Atmospheric Research, NCAR, which Dr. H also went there, as a postdoc fellow for 2 years before he joined OU in 2002. This experience has provided him a unique cross-disciplinary background of atmospheric research using various sensors. His expertise includes the development and design of novel and sophisticated radar techniques with the goals of improving radar measurement, enhancing the warning of severe and hazardous weather, and advancing the fundamental knowledge of meteorological phenomena. In parallel with his technical strength, he has a passion for delivering high-quality education. He has developed and taught several undergraduate and graduate courses in the field of radar technology and science at OU. Okay, so now the floor is yours. Thanks.
Okay, thank you. Okay, thank you, Barry. Thank you for the nice introduction. And first, I want to say that I'm delighted to be here. Thanks for the invitation. I'm very happy to have the opportunity here and to talk to you guys. I've been here for a few days. I'm very impressed by the students and faculty members I've met so far. Students are very high quality and very engaging, and the young faculty I met, they're very energetic and very motivated. So I'm really impressed. So today I want to take this opportunity to just show you some of the radar development and the applications in the Advanced Radar Research Center. That's where I'm coming from. Then we call ourselves ARRC. So the ARRC actually started, depends who you want to compare with. Compared to nationwide, this research center were actually relatively young. We started at the 2003, something from OU University of Oklahoma, their strategic radar initiative. Since just like you guys, we are a public school and the funding or the resources limited and all the time. So instead of spread out to invest in all different fields that time, our president decided to invest in some strategic area, the radar and the weather is one of them. And the reason for that is because of the special location and history that we have in Norman that many start with the NOAA partner, that's the National Surveillance Laboratory. They have in the past have developed this nationwide and next known as a NECRAD, this weather radar system. And at the same time, back in the 60s, that's when the meteorology program was established at OU. So since then, they've been working very close together. And that's one thing. And secondly, of course, you know that if you look at the frequency of the tornadoes, and Oklahoma is really in the valley. So we tend to have a very strong and very frequent tornadoes. So we like a nature laboratory for that. So we have kind of everything that we needed. So that's why it was decided back then radar specifically and the weather is one of the focus areas. So since then we have done quite a bit, so I'm not going through all the details. So basically the ARRC, the radar initiative, like I said, started in 2003. The ARRC that was established in 2005. First we start as we call ourselves Atmospheric Radar Research Center, because that time our goal is focused on the weather radar basically. And since then, a lot of things changed, a lot of things evolved. And in 2011 or so, we kind of get more mature in weather radar. So, if you look at the pie chart of different technology, I'll say weather radar probably like this, and the whole radar mostly will be defense radar. They are much bigger, area. But if you even do that, the communication can be even larger circle compared to that. So that's why we decide instead of focus on weather radar, we start expanding into more DoD type of radar system. I'll show you a little bit example of that, and that's where we have our new lab we moved in 2014. And there are a couple kind of things I want to highlight. The first one is if you do weather radar, there are two kind of the conferences that we always go to. One is more like a methodological focus. The other one is more engineering focus. So we host the AMS, that's more weather oriented radar conference in Norman back in 2015, and also 2018 in Oklahoma City that will host the IEEE, so more engineering focused radar conferences. So just show you a little bit about our people. So we have about 20 faculty members. So in a way, we are just like a traditional research center. We have faculty, we have kind of office staff, we have students, and grad student, postdoc, visiting scholars. This is very similar. And but one unique part kind of differentiate out from other more conventional research center. We have a technical staff. So far we have about 24 we have 24 technical staff. Those are the staff engineers and technicians. They specialize in different parts of the radar system. So some of them in RF system, in radar design, in mechanical design, in software, so all around the whole radar system. Then they're supported by a couple of project manager assistant office. So this is just kind of examples of a list of something that we think we're pretty good at it. And it's a wide spectrum of things. I'm not go through all this. So of course, we still do a lot of weather stuff, even though we expanded to more like a defense radar type. So so far our funding about 50-50. So about 50% of funding from more traditional science regime, and in weather, the other half is about, I would say, from DoD, from variety of DoD and private company. So I don't know. So for some faculty, if you're interested, our current active funding is about $80 million. So just give a kind of scope of our kind of research center. So one thing we're kind of proud ourselves is that this is we call so-called cycle innovation. So this is kind of our practice and how we develop radar and what kind of our philosophy. Basically, we like to have this kind of well around this concept. Some more traditional kind of radar, research center, they may only specialize in one of the system, and very few they can build the whole system. But even though they build system, they don't feel it. But for us, we really start with the concept. So there are a lot of agency or funding sponsors or private companies. They will come and discuss and talk about their needs. Then we'll kind of brainstorming, come up if the radar makes sense. Not necessarily all the time radar makes sense. But if your radar makes sense, then we come up with the conceptual design, what kind of system makes sense, and some kind of property and so on and so forth. Then with different faculty that kind of focus on the different spatial area, that we have very strong in antennas and especially phase array antennas and some of the RF system, RF components, like filters and backend digital receivers. And the whole thing is that we can do this very rapidly. And the fast radar system we build probably within 3 months. So, but that's a smaller one, not big one. The bigger one can take 5 to 7 years. So it depends on the system. But the point is that once we have the system, we'll not just stop there. So most of the center, they have system, they hand it out to the users. But we don't. We do have faculty members that from meteorology or from civil engineering kind of focus on the hydrological application. They actually take the radar out, collect the data, then we develop our own signal processing algorithm you can implement on the radar system right away. The key is that once we learn all this, then you always will find something in the system that will have something you can improve. So you kind of go back and start this cycle again. Then you kind of think about there's certain things we want to improve and even build a new system. So that's what we do. So this is kind of our model to build things. I'm going to show you a couple examples that this is what we do. So even though we're a research center, but most of our members were just regular faculty members, in the either electrical engineering or in civil engineering or in meteorology. So we teach classes, we advise students just like a regular faculty. So here just a suite of classes that we offer throughout curriculum. We have a very specialized radar curriculum that can offer these classes. This is not quite updated yet, but we have more classes now. But you and I only take these classes directly, so you actually have more fundamental classes that involve electrical engineering and meteorology. Once you have that, most of these are more advanced, classes, but that allow you to take in the different flavor. I know many of them kind of focus on the engineering side. That's another special feature about all this program that, so our center, like Dr. Wayne just mentioned, it's interdisciplinary. So we have students coming, I think mainly from three departments: electrical engineering, meteorology, and the civil engineering. They are doing the hydrological applications. So there are much stronger tie between engineering and meteorology. So we have students kind of taking courses back and forth. What happened more often is actually a little bit one-way street, is that we have a lot of PhD students that getting a PhD in the meteorology, but at the same time they're taking many engineering flavor classes, so such that actually they can get a master's degree in electrical engineering along the way. So just kind of give you some flavor that they are not just pure science, pure meteorology. They do have a lot of hands-on experience. They have a lot of knowledge in terms of radar in front of engineering side. So that the goal is try to create an environment, different disciplines really respect and appreciate what other people are doing. So I think that's kind of our message we want to send out to the students, make them, appreciate each other. So we don't want meteorologists say engineers working for me. I just tell them what to do. We don't want engineers say, you don't know anything about engineering, why you're talking. So we want to have that communication that can, flow back and forth equally. So that's what we're shooting for. And at the same time, we have several fellowships that can kind of offer to students either in the DoD side or in the meteorological side. So I just mentioned that since we have a lot of radar systems, so students have plenty of opportunities to play around different parts of the system, depends on their research focus or different classes. So that's kind of the other kind of aspect of our curriculum. So this just show you a quick chart that where our students went after they graduated. So they went to all different places. I don't know how many that you recognize, and you probably know Tesla. I think there's SpaceX. There a whole bunch of other stuff. There's some of them local, some of the big defense companies, Raytheon, Lockheed, Northrop Grumman, and Boeing. And some more private. MATLAB, you probably know MATLAB, and of course many of them also continue their academic, ventures. So just kind of give you some idea. So I did add Microsoft for because Dr. Wayne is here. So he was state PO before, but yeah, you're right. That's a good point. Next time I animate it. Right? Depends on where I'm going. I should animate this something. Okay. I remember that comment. I will fix that next time. Okay, good point. All right, so this is like maybe a little bit boring to you, but the point is that we have faculty that publishes several textbooks in our radar field. The other part is that maybe a little bit more from DoD side that every couple of years we have the industrial government days. This is fairly not released a couple of years ago that we just bring all the industrial partners inside here. And they can kind of learn what we're doing at the same time. Now we actually have a formalized program. Yeah, the Spark. This is actually this is like a consortium. Company can pay the annual fee to be a member of that, but they can access our student resumes and early publications and research products and so on and so forth. So this is something that relatively new that we just recently doing. Very quickly, once we have all this kind of soft part, we can go software of our center. But here is like a hardware of facilities, and so we're growing very fast. So this is our first building. It's much larger building, 35,000 square feet, and complete 2014, but very fast we kind of have hit a wall. We don't have enough space. And recently, this one is complete recently. Then last year, then we called Real Annex, and some of us more, loose way we call Real 1.5, and actually we're building another one called Real 1.6 now. And one of the reasons to kind of pushing all this kind of smaller but cheaper building in a way is that because we're start doing a lot of kind of ITAR control. It's not, not classifying away, but it is a control project that restrict the access of some of the product that we've been building. So that's why all these buildings become kind of controlled. But it's hard to control this big building because we do have other side, like a weather radar side. There's really no control. We have a lot of international students. They go around. So that's why we start having a different separate places that. And, a lot of this DoD funding, they require you to have a secure place before they can give you funding. So here, just maybe more interesting, I should show you, this is just kind of the video of our building. This is the big one, the small one, we don't have a video yet. So this is the outside of the building. So this is one of our echo chamber that used to characterize the antenna performance as well as the measuring the radar cross section. So all these are related to the radar system. So we have two of this. One is bigger one is a smaller one. We have an even bigger one that can actually drive the truck inside this chamber area to test all the antenna that we're building in this Real 1.5. So this is our main student area. So it's an open space. So we have two different setup. One is for master student, the other one is for PhD student. So they all kind of sitting there together, try to promote their collaboration within this open environment. So given all this, and just want to show you a little bit some of the examples what I'm going to show you in terms of the radar technology or related to radar technology in ARRC. Before that, I just want to show you some of the this technology map that we have. So you can sort of see the timeline that the early days we have more dish-based antenna. So you can see this picture is Rexport, the radar that we brought here a few days ago. And then about mid-20s, 2000s, we start building our first phase array antenna. So I would explain what phase array antenna is. This particular one called AIR, I'm going to show you some data later, include this animation. And this is another project that we're working on. So this is kind of the early version of the phase array there. I'll give you another example to show you what that means. So this is a phase array, but it is an older technology in the phase array. And there around the 2015 or so, a little bit later actually, then we started moving into the more advanced phase array technology. It's called a digital phase array. So this is a newer version that we're building, and first it's supported by NOAA for weather observation, but the radar itself, you can do weather, you can also do military. It depends how you want to use it. That's why the line is become really blurred. And this is I'll talk more about this particular system. So first was designed for weather observation, but very, very fast. The DoD is knowing that we have such a system, in the development, so they get really interested. So later, the Army and the Navy, they become really interesting. So we're building slightly change of the design, but we're building system for them too. And of course, this is some kind of future goal. We want to take this technology should expand that to become, let's say, potentially, this is me talking, right? Potentially become the replacement for the next radar. So that's kind of our ambitious goal, but we'll see how that goes. So the reason we can do that because later I'm going to show you that the whole system itself is really modular. We have these building blocks. If you have large radar, you start putting more in there. So things become a lot easier. So this may be a little bit hard, or maybe you're not familiar with what phaser or what traditional dish antenna is, but you can sort of see dish has this really large antenna size and kind of bulky, and the phase array is kind of planned. So this advanced phase array is also planned. So I don't know, I try to use another example, maybe you're more familiar with. And if you look at the display technology, So I don't know how many of you, especially students, probably never see something called CRT, right? For us for sure, yeah, we grew in that.
Folks have to remember that.
Exactly, yeah, so very tiny TV, you type in resolution and bulky and, so you guys, at least you guys know what the LCD is, right? The liquid crystal display. And now more advanced one, more expensive one, of course, is this OLED, this organic light emitted diode. So both of these, they are kind of flat panels, but they're actually very different. So the first one, let's go back to this one. So you can easily Google that. You probably can go to eBay to buy one of those if you're interested. Just try to play around with this. So you can see it's a curve, it's a bulky. You have this really long, this emitted stuff over there, and then really poor quality, but it worked. That's how we get it. So later on with this LCD, you still have multiple layers to make it work. And this is really the backlight. That means you have the many pixels. They are very fine, but each pixel does not, it just reflect, they'll pass through whatever the backlight. So you have one light sources that kind of illuminate the whole thing and try to come up with this picture. So they can make it flat. But the difference between the next one, this OLED, that each pixels, if you know the technology, you know each pixel, they can generate its own light. So that's why it has a higher contrast. It can have a high brightness and so on and so forth, have this advantage, or even also make it more thinner. So the reason I want to make that, in this OLED technology, you are able to control each element, each pixel, then to do its own, to change the color of each pixel. So the whole all digital phase array radar. So the older fashion is really like this LCD. It's just one big transmitter. So you have many elements, you just blast through the energy, and there's a plumbing, then goes through that, and the signal will go out. So for the all digital, it's different. So for each element, so for this particular system, you have 1,024 elements. We can control each element for transmitting and receiving. So it's really like you are putting 1,024 radar on these little panels right here. It's still really thin. So I can show you some pictures. So I just wanted to show you the difference. Even both of these are the phase array. One of that, the one we built early on, they have we don't have much control of the system, let me put it that way. And this one, we just have a full control of the whole system. Hopefully this one can give you some idea about what these two systems will look like. So, and this one, the potential of phase array, this is a kind of stole from one of our proposal, which is it's not get funded, but anyway, so this is what we put in there. And this is we try to apply for this National Science Foundation mid-scale, this big proposal. This is try to use a comparison between two types of, I was gonna say mobile radar in a way. So if you have a smaller mobile radar like a RESPO we brought here, it's X-band. And this one is what we propose, we call TPAR. It's called a transportable phase array radar. So it is an S-band. So if you don't know, X-band is about 3 centimeter wavelengths, and this S-band radar is about 10 centimeter wavelength. So it's larger. So all the system is large. So this is a much larger system. But this one will build upon an all digital, architecture. So some of the comparisons still relevant. For example, the biggest advantage of the phase array is really the temporal resolution. So the difference between this conventional one, later you'll see the video, is that you have an antenna, right? So it's mounted on the pedestal, so mechanically you just rotate it around. So you can rotate from like RESPO very fast, but still you still have to make it move in a mechanical way. But the phase array, you have this flat panel, right? So it's basically, if you want to change the location, where you want to look, change the beam location, you don't have to rotate. The whole thing can be stationary, but you can control the phase of this element. That's why it's called phase array, right? So can control that such that the beam can be steered at a different direction electronically. So that's why if you can control it electronically, everything can be done really fast. When I say fast, I mean in the time of millisecond if you want to. So not in a second, millisecond. So you can do this really fast. You cannot imagine that mechanically, you want to do weird things. But if you want to do this, that's really not much benefit. So here we kind of calculate that if we really do a full phase array, like the system we propose, it can be 15 times faster. So when we say 15 times faster, we don't mean, when we talk about fast, is sometimes fast is not the whole thing because a lot of times if you fast, you're actually going to compromise the data quality. So here we assume the data quality is the same, but you can do 15 times faster by doing other things. And also this, you have a kind of relative poor vertical sampling because when this is a constraint, how long you want to cover this particular volume. Then if you spin around, you elevate, spin around. So if you want to sample this in elevation in a fine scale, then you have to cover more. That means you have to do more spins. It takes more time. But if you want to cover that volume, but at the same time, you don't want that take that much time, then you have to skip some of the elevation. So therefore, the vertical coverage, it can be poor. Okay, but in the phase array, there's a different technology we call digital beamforming or the imaging. You can send out very wide beam, then, or you can try to think about, I'll go detail. So you can try to think of, we can send it out multiple beams, hundreds of beams at the same time. They'll all the signal come by the same time. So we can have as fine coverage as you want. Then the whole thing can spin around. So that's why it can give us a lot of finer temporal sampling. So the next one is not quite fair comparison, but because we also developed another technology called the multi-static wind retrieval. And most of our radar system can only measure the radial winds. That means the projection of wind inside the beam pointing direction. But now we are putting some very cheap receiving antennas such that we can get a 3-dimensional wind. So for a lot of observation, vertical wind is one of the biggest information that we're lacking, especially use weather radar. So this one definitely can try to mitigate that. And the other one is that this is the difference between X-band and S-band. But the other part, the important part, not just temporal resolution of the phase array, one thing I want to emphasize, so the biggest benefit, I said, one of the benefit phase array is the flexibility. Okay, so it can do what conventional radar does, but it can also do what conventional radar cannot do. Okay, so because some situation you really don't need anything fancy. Let's say you have a stratiform precipitation, everything's uniform, moving slow. You can't just scan slowly. You don't gonna gain anything by see do all weird things, right? You can do that. So phase array can still do that. Don't think phase array can only do fancy things. You can do simple things too. So it's really about the flexibility. But when there's needed, let's say when you have a tornado, then you have other potential location. Let's say a multi-cell. So one of the cell maybe produce tornado. The other cell maybe produce tornado, I don't know, 10 minutes later. So if you scan, with the same rate, like a conventional radar, you might miss this one. Okay, so for the phase array, what you can do is that, let's say there's a tornado, you definitely want to look at it more often. So you can come back, look at this. Then you also know there are other potential, you can go back, less often. Some of them is not potentially hazard. You can even look at it every 5 minutes or so. That gives you the different flexibility of looking at storm differently. So that kind of opens up, you can say research potentials, or you can say came out warrants that how you want to use the data. You can try to imagine how you're going to use the data. First, for the operational forecast, it will be nightmare for them. The data is not becoming uniform anymore. It's going to be all over the place. It's not going to synchronize in time, in space, right? So, and even for the data simulation people, they don't like it either because one is that we are updating the data can be on the order of seconds. So they are looking at instead of minutes or so. And also this non-uniform in the space and time. This is something that we have to deal with. But always a challenge can turn into opportunity, right? So all this can be potentially a research topic for if anybody that interested in this particular field. Okay, so I'm going to spend rest of my time just talk about some example of the ARRC systems, and just ask me any questions that you have. So this is the first system we call PX1000, and this is this cycle innovation we talk about. So from the design, construction, we validate the data. We take the radar out to do all sorts of different outside to do a field experiment. Then we analyze the data, then do so on. So this is a very little tiny system. It's a portable one, so the truck can just pull it. So a few days ago, before we come down here, actually we just took it to do some wind farm study. We want to measure the wakes from the wind turbines and so on and so forth. So just want to show you another kind of, maybe you're more interested in looking at data. So this is when it's in become experiment. So some of you probably know this is a tornado images from radar. So this is from PX1000. For this particular case, we were lucky. We only scanned one elevation. I don't know why, but that we're lucky. We only scanned one elevation. It's 25 seconds update time, so very fast. So you can see very nice tornado moving in those locations. So this is a very EF5 big tornadoes. This is one of the largest one in Oklahoma. So I just want to point something to you. So this is where the tornado is forming, right? So you can see this little fly looking, right? So kind of flying in front of the tornado. Can anybody guess what those are? I always like to ask this question to my audience.
Flock of birds.
Birds, yes. The birds, they typically don't fly in front of tornado. Something like us. Can you imagine when tornado forms and evolve, something really want to stay in front of tornadoes? I'm not saying it has to be nature, right? It can be something man-made. Car? This is really in the sky, but yes, it's helicopters. So I think your TV station here, they are also always interested in the storms, right? So those are the Oklahoma TV stations that there are two helicopters. Every time there's a tornado, they want to stay ahead of the tornado, give you the real time, visualization of the tornadoes. So that was so here I just want to let you know that, radar can see weather and, helicopters, airplanes, missiles, we can even see birds and insects. I'm going to show you later. Okay, so this is another example that some of you in the short course, you probably heard about this already. So the problem of this one is that in Colorado, there's some burn area. So the fire, the forest fire, they burn down some of the area. So those are scar area that very susceptible to floods because you don't have any tree anymore. So once there's a flood, when there's a big rain coming down, they can create a lot of landslides and so on and so forth. And just because the terrain, the topography right here, there are a couple of big radars, the X-ray radars. It's about 200 kilometers away. So Earth is not flat. You have mountains. So those kind of valley area, the big radar cannot see. So that's why we brought these little radars go over there and see. So the reason I want to show these pictures, I think one of the talks mentioned, I think Pierre's talk, this guy Stanley is the manager of the local emergency management. So he's the one in charge of the radar because the whole radar is designed for an attendant. And it's very easy. You can even remotely control it, just like a Rexpo. So because the reason I include is because he was so proud he can actually run the radar. So I just want to say that the radar design, not just the hardware, software part, we also, make it really easy. So honestly, it's really easy. If you don't want any trouble, all you need to do is just run. But you are running a radar. So in the next week, we do have a student-led experiment. If you're interested, I think there's the opportunity to sign up for you to experience how to run the radar system. So here is just a very quick demonstration of what you can see. So this is that little radar. You can see in this particular area, you see a lot of precipitation system. But for the bigger radar, let me just wait for a little bit when it starts. So you probably can see the one you see because the little radar see here, the large radar actually seeing something up there. So they are seeing different things. And what worry the people locally they live there is really worried about what happened down here, right? So the big rain and everything. So this sounds easy, but little radar does solve this earth curvature and the terrain problem. So this is kind of the cycle innovation just because the success of that previous example. So now we have built the next generation, then with a bigger antenna and higher power. And also build our pedestal here. Just want you to see how fast this pedestal can rotate. This one rotates as fast as the Rexpo we have. It rotates 180 degrees per second. At one point, it can do 360, but recently I don't know why it does not do that job. And use the direct drive. You probably heard about this term, like direct drive. Now the motors, I'm saying like Tesla's cars and some of your washing machines, they use direct drive. So this is also used direct drive. There's no gear in there, so you don't need to worry about the wear and tears of all the gears. So just kind of show you, this is the next generation of the PX1000. So maybe one thing just kind of a little bit geeky. So the previous one called PX1000, this is called PX10000. So P is stand for polymetric. This is the particular type of radar system. X is the frequency band. This is the X band. So the previous one, the reason it's called 10,000 because that system was built in 2008. Do you know what 8 and 1,000? Any relationship? Exactly. Good job, Steve. So the binary of 1,000 it is 8. So that thing, then you can guess 10,000. It was built in 2016. So just happened to be that way. And recently I got asked a question, what happened to the next? I don't know. I mean, we'll see. That's always a fun part. We can always come up with different names. So this is the particular radar system that we brought right here. It is another X-band radar and can rotate really fast. And this is just some of the images that the radar images that collect by the data. This is a while back. And the Rexpo has been used for different applications. So here, maybe just let me show you some of this. So this is a really fresh out of the pod. This is a couple of days ago, 13 couple of days ago. We took just a little south of Gainesville to do that. I think I took this one as a video. So you can sort of see that the radar is moving. And this is one example data that collect, not corresponding that time, but of course, collecting data we call ARRC mode. And this is what the return data look like. So I don't have a sound here, but this is a example of we took the Rexpo to New York in this February to do winter storm experiment. You can see, probably a little bit hard to see, you can see our waveguide got a lot of snow, it's so frozen. And to a point, actually, one of the channels did not work. So because we never took this radar to such a kind of challenging place. Okay, so you probably can see that this is a biport. And what they told me, I did not go this time. So what they told me is that you can see all the wind blowing right here. Actually, the ocean waves actually coming in that they flood out half of the tire. They couldn't even get to the radar. So
how do you overcome these challenges?
Okay, that's a good question. So at this point, no, we don't have any way to overcome. So some people think about we can have a hair dryer. So that's actually one. You'll be surprised. That's a lot of time engineers do very practical things, right? And we thought about bringing some of the heating elements over there. But we do have a solution. That's next time when we position the radar, we don't want to put it in the downstream. So we want to position the radar in a different way, such that the snow will not directly hit the back of the radar. Instead, it will hit the truck. So that will mitigate some of those. So we're going back to there again next year. So it'll be interesting to see that if our engineer come up with any novel ideas other than hair dryer. And it was so cold. I was told that you cannot, and very windy.
Perhaps use a different material. There is a lot of research going on in nanomaterials.
Yeah, I don't know. We can afford it, honestly. So yeah, well, sometimes we'll probably try some brute force wave first. Then that that require that will be, if you come to OU, then that will be your research project. Okay, let's do that. So all these are brainstorming that those are good ideas, but we just have to try one by one. Hopefully, one day that one of the solution works. So another interesting part, you can see this is the sun radar. We're not just observing the weather. Here is just convective storms and winter storms. We do that, use the radar to see birds too. So and insects too. So the radar is sensitive enough. You can see birds and insects and bats and all these different kind of flying objects. So that kind of bring into a different type, not using this radar. So this is a kind of mosaic composite reflectivity from the nationwide X-ray. So this is what you typically can see. If you go to NOAA web page, this is what you see. As you can see, this is United States. There's a swirl line. There's some storms over the whole U.S. So it looked very nice, right? But this is after data quality control. So we kind of acquire what happened before data quality control. It's not as good as it looked. And a lot of these echoes, they're actually coming from the biological. So they are actually migrating birds or insects and so on and so forth. So you would think, this is something I always kind of encourage my student. Someone's clutter can be your signal. That's how weather radar was developed. The radar was first developed for military, right? So when they run the radar, they say, hey, what's this one? That's really annoying. I cannot see my airplane. It turned out to be weather. Then the meteorologist say, hey, that's nice. I can use radar to see weather. Okay, so good. So the similar things right here is for weather people, they probably find this very annoying. But for biologists, they say, wow, that's really good. I can use this kind of data to study the bird's migration pattern and how the disease may be being transported. So you open up the whole thing, but they need to go into this kind of different kind of raw data in order to do that. So this is just something, a specific things that we call the radar air ecology, basically use radar to do this kind of observation on flying birds. Those are some of the flying patterns that they come up with this cartoon. So one experiment they're doing is that not just to use the radar, you saw the radar, they also took the infrared over there to do the experiment in collaboration with radar. And at the same time, you need some in situ measurement. So I don't know if you can see, maybe it's a little bit dark. So this is a bat. Okay, so it's important. So radar is a volume measurement, right? So when you scan through, you try to, everything you measure is being averaged within its volume. But you want to know, for example, how many birds or how many bats inside this volume by looking at your received signal. So first of all, you have to know how many. Typically you use infrared, kind of know where the volume is. Hopefully you can estimate how many of them. But you also want to know for each one of them, what kind of signal they can give you. So you need kind of quantify. That's why we took this bat. This was done maybe 15 years ago. So this was back in the day. So somehow the student was able to capture a bat, then just tie into this string and try to put it into, that time we don't have a nice anechoic chamber. So they just put in there, then try to measure the radar cross section, especially the flapping, wings and so on and so forth. And just don't worry, they released the bat after this experiment. So the bat
stressed out.
Yeah, well, yeah, sorry, bat then. Yeah, definitely stressed out. I don't think any bat, would like that. Yes, yeah. Okay, so this is a totally different technology that I just kind of briefly talk about. This is atmospheric image radar. So typical radar, you send out pencil beams going around. So like I said, you want to scan many elevation, takes a lot of time. So this particular radar, they are able to transmit a very wide transmitting, sort of like your camera, right? So let's say if you're in a dark room, I want you to find something totally dark, pitch dark. And one thing you can, if I give you a flashlight, you probably, what you would do, you take your flashlight, it takes time to find it, right? So, or you can take a picture of the room, then you just find it. So how this picture works, you flash, right? You illuminate the light, then receive by the pixels, then you look at the pixel. So the image radar is like this. So you illuminate the sky by transmitting very wide beam, kind of illuminate the electromagnetic, but upon receiving, we have 36 independent receivers. So like this pixel, they receive the return signal. Then you can process them such that you can form the finer pixel, just like a camera. So that's why it's called image radar. So such that you have everything inside this is just one snapshot instead of just one snapshot. So it can become really fast. So this is one of the storm that collected. So let me show you this example. So this is when have image radar not moving, because that time the whole thing was built by a student, by the way. And then we would just point at, so the radar is sitting right here. It's pointing at a cold front is coming toward the radar. So this is the distance. This is the height. The top is the reflectivity. The darker the color, the yellows, the more yellow means more strong return. The blue and the green and the red, the blue, they're kind of lighter. And here is the radial velocity. Kind of tell you how the gust front is moving in. The green means it's moving toward, and the red means moving forward. So I just want you to focus on, just for fun, just look at the shape. And by the way, the update time is every 1 second. So give you very, very fast update time. We can even lower the, or I should say, increase the temporary resolution to maybe 0.1 second if we want to. But there's always a trade-off. So I don't know, you had the chance, I probably talked to Mike, you have a chance to see what happened right here. So for some of you, knowing this probably better than I do, those kind of called a Kelman-House instability or billows. So, or if you don't know this, you probably see how ocean wave breaks, right? So you basically going like this, for the surfing, right? So you basically going down like this, start from the turbulent, become a circle. So this happened to the atmosphere too. Then we're able to capture such that, and the reason we can see such a nice evolution of the whole event, because we have very, very fine temporal resolution and the spatial resolution too to see that. This is kind of because the success of that one is a single polarization. And because our success that we were able to convince NSF, the National Science Foundation, to give us another chunk of money to build the next generation. It's become dual polarization, still the phase array. And this is kind of next generation of that. So so the first one is going to be a dual polarization. Then we kind of move from X band to C band to a little bit longer wavelengths, because we wanted to be able to have a better penetration of the storms, like we want to see hurricanes and so on and so forth. So that's why we move out. So by given the sacrifice of the beamwidth, the angular resolution is going to be reduced a little bit. So this can have a two operation. We can do the imaging, but we can also do the pencil beam if we want. So it has very high sensitivity. So because of the temporal resolution that you can gain, so this one can go around probably in the order of 6 to 10 seconds, give a 20 degrees. So you can think about 360 degrees by 20 degrees in about 6 seconds. So that's very, very fast. And of course that people so far are showing interest in doing let's say the severe storm observation, like tornadoes and the hailstorms and the boundary layer rolls, like in the hurricanes. Now, of course, we recently wrote a proposal, use this particular system. It's still almost done, but not quite yet. But we're going to use this system after it's done to do the lightning study, electrification in the cloud, because that things happen very, very fast. But this one has the kind of enough resolution to resolve that. Now, of course, we're going to take to do some of the biological studies. So this is just a current that we already finished all the array structures. So those are the phase array flat panels. So totally we have 76 these 8x8 panels that put together. Just show you some picture of that. So you don't need to worry about this sensitivity. So this is the next kind of advanced radar system we call all digital system. So like I said, so this particular system has 25 panels. Each panel have 8x8 elements. So totally have 1,024 elements. So each one can produce 10 watts per channel. So again, both of these are phase array, dual polarization phase array antennas or phase array radars. So like I mentioned earlier, that the unique feature of this one can sample at each element. So each element like this big. So it has its own transmitter, receiver, and everything. So everything come out that was just the digital signal. So because, so the beauty about digital signal is that if you want to have a higher power, you just, in the MATLAB or whatever, times 10, you just increase by 10 times. If you want the filtering and everything, you just do it in computer. So this one is more like an ultimate hardware that you need for this particular application. And you open up that how you want to do for this particular panel, you can control that in different ways. For example, I can divide the panel into 4 parts, and each part point at the beginning in a totally different direction. I can do that. Or that what the military sometimes they're interested in is I maybe want to carve out some part of the antenna to do communication, not radar. So all this kind of multi-function capability kind of open up a door for a lot of research. Even something I'm very proud of, in radar, most of the time, military radar, they are always more advanced than weather radar. But in this case, that weather radar development actually is ahead of the military radar, just because we are doing a lot of phaser technology in the dual polarization. Military, they don't care about the dual polarization yet, but they start to realize there's some additional information that they can use in terms of for their purpose. So that's why the DoD people getting to use this. So this is just some nice animation that we did. So this is the truck. So this is a much bigger truck than the truck we brought. So you do need to have a CDL, commercial driver's license for it. This is something we struggle. We have 3 trucks. We only have 1 person with the commercial driver's license. So because recently they changed the rule that you have to go through this 1 month training that nobody can do. So I don't know what to do. So you know, sometimes it's kind of interesting that, you know, technology, we're doing all this, but we don't have people to drive the truck. So you go figure. So this is the kind of real time that to show you that. So this is before that we put everything. So this is what the truck looked like. Previously is a rendering. So at least you can see that truck. Then we start putting the phase array on the back out. So all this there are the enclosure for all the electronics. So here just kind of zooming feature. So we only put one of these. This is 1x5 sub arrays that in this particular one. So I'm just going to, in the interest of time, this is something we propose to go, because this one is a kind of building block. We can go to much larger size by adding more of this. So the design of this one is has the capability to add more. So it's really like a building block for the largest system. So I'm going to skip this one, and yeah, I'm going to skip this one. So I just want to show you something more interesting that it's related to radar and not just the hardware. I think I show you a lot of hardware, but in software, in terms of simulation, I don't know how many versions of radar simulator we have in our center. I would say at least 5 to 10, but this is just one version of that. So the idea of that is we want to generate a very, very realistic radar simulator. It means what happened out there, I want to have a realistic, you know, radar signal. When I say radar signal, I mean the raw IQ, the IQ radar signal. It's not even the moments reflected, you know, very, very raw radar signal. So in order to do that, there's different way we can do that. And for this particular case, they also specifically interested in the debris inside the tornado. So what they're doing is that they take a numerical model. So in this particular case, they can use the large eddy simulation that give you the wind fields. So inside the wind fields, and they put a whole bunch of scatters. When I say whole bunch, I mean tens of millions scatters in there. So each one, so for example, this is just an example. When I say just one leaf, there are millions of leaves here. So one leaf, when you fall, right? So you basically can do something like this when you just free fall. But whenever you do this, the radar look, you actually give a different amount of signal to radar. So we all try to characterize that. In the same time, this leaf fall, if you have a background wind, a tornado, so I don't know, so you do have whatever the motion is going to give you. So we try to simulate to such a detail of all these debris. So I'm just show you some nice animation that. So this is just give you some idea what you can see. Those are the orange one. Those are the raindrops. I cannot really read. I think something on the order of million raindrops. And what you see, the green one are the leaves. There are different types of leaves. I'm pretty sure if you see the larger one, those are the 4x4 plywoods, assuming that whatever debris that you can have inside the tornadoes. So this is just, you can sort of see the circulation of the tornado. I think the wind field at this point, I think this is from the large AD simulation. So this one, each one of them, basically you have radar energy going there and then generate a radar signal coming back. So this one just give you a different point of view, different rotation. When you have radar beams scanning through that, this is just a zoom-in version that's looking at different parts of the storm with the debris as well as the raindrops, what the signal will look like. So the reason of that is that if you want to study how debris is going to impact the tornado, through this simulation, what you can do, you can see what tornado will look like without debris, right? Then you can start to add in different type of debris. Then you can start observe how the radar signal, even the phenomena, how the phenomena changes in a very controlled manner. So that's the whole point of this simulation. So this is just a different way of scanning. So this is in the range direction. Okay, so that's all I have, and hopefully you guys finish that in time. So thank you very much.
What? Of course I have a question. I'll start with your simulation at the end. I can give you some ideas about birds and insects.
Yes.
I come from a background biology.
Mhm.
You know, some funding that's been made. But does the new phased array radar really? I'm going to say this, and you agree with me or not. Has incredible potential for tracking animals in the sky.
Yes.
Much more so than anything we have now. And the aerobiologists now can't identify birds down to species. They can tell big birds from little birds,
Mhm.
like your bat.
Yeah.
But could they do that? Is there a potential for doing that?
I think there's potential doing that, but not so much on the phased array. Dualization that can do that. That does give you they have certain product that the combination of those product, there's a potential to distinguish different species.
Yeah.
But the complexity comes in that when they fly in different angle, the signature may change. So the whole thing.
That's like the leaf falling.
Exactly. So the signature can get confused based on their orientation, based on how radar look at that. Some people start looking at those. They are able to. At least one of my students, he wanted to just separate the regular birds and bats. So he's doing some of the AI techniques, try to look at the radar product, try to separate those. I'm pretty sure you're able to further look into down a little bit more detail of the different species.
I worked at NSF for a while. We funded 2 aerobiology.
Oh, really?
projects to use NextRad data.
Yeah. So you probably know the chosen that. So he researched.
So why won't the phased array be as good or be better than what's the limitation there?
For the phased array, I think in the operational setting, I don't think that other than give you fast update time from that particular operation, I don't see phased array really give you much. But in the research mode, I think phased array can give you better tracking capability.
Yeah.
Just like you want to track, military missiles and so on and so forth. You are able to focus, let's say you do know, let's say your whole goal is track specific birds. Once you identify, the phased array can dedicate its resources to do that. Then you can get much better interrogation of that particular route. So
yeah, because if you want to know the birds, you want to know the shape, right? So the polarimetric, which means horizontal and vertical, can give you more information. For phased array, like next generation is like scanning faster, or we can do like targeted scanning, right? So it's not about the shape. So now we put the polarimetric and phased array together. So it's very difficult because phased array will change the beam, and if you add the polarimetric nature, so it's not perpendicular to each other, right? So yeah.
Too many axes.
Yeah, exactly. So we are doing the experiments in the moment. Yeah, I can forward my paper to you.
Of course.
So, but it's a way.
We'll
Yeah.
continue this conversation.
Yeah.
later. Otherwise, I'll dominate the whole question.
Okay.
Yeah, along these same lines, we have a lot of folks here who are worried about either disease vectors or conservation or even conflict overseas. So we use a lot of remote sensing from satellites. We got a couple of radars up in space. If those are being used for non-weather research things right now?
I don't know anything about that. I don't think they have a sufficient resolution, spatial resolution to see what ground-based radar can see. So
Yeah, that's what I didn't know is exactly what their specs.
yeah, there's, I don't know, 2 kilometers. The finest one on the ground that footprint.
You mean
The radar.
Yes, you.
Radar.
Well, that's the.
Oh,
Based
okay.
on radar.
It's like 4 kilometers from DPR to 10 DPR, 4 kilometers. Level 2 for that.
So we get down to 100 meters. Sometimes it can be even finer.
And I do agree with you. There are a lot of satellites, and we use a lot of satellites for the disease control thing, but really for ground weather radar. And one reason I want to point out is ground weather radar is like more difficult to use. As you can see, it's like the cone shape. Yeah, even when I was at the JPL, not all of them know how to use ground weather radar there. Yeah, so they think it's a scale. you need a skill set to use ground weather radar. So which means if you know how to handle the ground weather radar, you can find a good job.
So please take Dr. Wen's 4410 radar and satellite meteorology class. He will teach you how to use radar.
Yeah, I have a question. So ARRC has so nice and with several nice radar systems, and we have a lot of data sets, right? Are these data sets open to our students?
Yes, I think some of you in this morning's radar hub, that's how it goes. So we are heading to the direction we want everything's open, and we want our source code, it's open source. And we'll put on there, you guys are welcome to use it. And we build that upon the, this open source architecture. And our goal is our data, we'll try to make them available. The data we collect, we'll try to make them available as soon as possible. Some of you probably see that it's actually real time. You can see that. Okay, but the thing is that with some other people that not in the ARRC, they can also request to use our radar system. Everybody has a different data policy, but we kind of force them, at least you need to publish your data within a year to the community. So if you don't, we will. So they can. Okay, so because some people, it's quite a bit effort for them to, assemble teams, then collect data. They do want to have first step. That we respect that, but we don't, So if you want to compete with us, you can collect the data then. But just a word of caution that because we want to do it fast, so the data may not be in the pristine shape. Okay, so use with cautious. They will have some contamination like interference. Cloud may not, fully remove these kind of things. But you can have the first look and what the data will look like.
Don't worry, we'll find complaint to you.
Okay. Okay. And she has my email, so just send it to me.
So any questions?
Thank you for your presentation. I was thinking, has anyone ever thought of implementing one of these radars in a vessel? I kept thinking about weather and migrating patterns and implementing like a wind farm in the ocean. So it may acquire very relevant data.
Okay, that's a very good question. So why I say good, because I'm involved in one of the projects actually doing that. So I'm working with a kind of private company in New York. They are working with GE with the offshore wind turbines. So now we're trying to explore the potential of putting radars inside the wind farm, offshore wind farms, try to measure all the wakes information, as well as I think they're talking about 4 kilometers around outside the wind farm in terms of the weather detection. So we're doing that, but it's a very, very challenging problem. So the wind farm, you think, it maybe look cool and everything. For radar, personally, I really hate it because it creates such a big interference. You can think of the pole. I don't like it. I want everything other than wind farm. So that pole gives radar very large return. It's bad, but pole is not too bad because it's stationary. I can remove that red easy. But the blade is the problem. The even worse, when it rotates, it gives you all sorts of velocity. It's not just give you one point I can remove. It spans out the whole spectrum. It's almost impossible to remove. So I should say there are ways, but it's not very easy. So it's kind of, even currently it's a universal problem for all the radar try to deal with the wind farm problem. So it's very difficult. Yes, please.
Thank you. So with the radars, sensitive for elevation, like coastal area elevation, the laser and the mountain region, sensitive.
So you're talking, if I understand, so radar itself does its own thing. When you say sensitive, I think you're meant can radar observe in those areas, right? Okay, so you can try to think about, I'm a radar, I'm sending out a beam. It's just like a flashlight scanning through. Whenever you hit a person, you won't be able to see whatever behind. So radar does the same way, scanning through. If a mountain in front of it, you won't be able to see it. If you have something very close to radar, whatever, let's say radar right here, I'm blocking out maybe 20 degrees. If I'm further, maybe 10 degrees. So that's just a physics that, so where to put a radar become very important. So that's why, some, let's say in the United States, the challenge place will be the Rocky Mountain area because, you know, you just have a lot of terrains and everything. There's a lot of blockage. And that's Dr. One they've been doing. That's try to use the satellite data, try to overcome some of the problems. So, yeah. So I will not say radar sensitive or not sensitive. It just whenever it got blocked, it got blocked. So it will be interesting that just
Some Martians produce like elevation sensitive around the coastal area, maybe Bombay, mountain regions and many.
yeah, it depends on where you are at. So for example, that you know, I went to a lot of Asian country to visit in South Korea. They put their whole operational rate up to the mountain, but the price have to be ×3 because they have to use helicopter to move everything up. Depends how much money you want to put in there. So that's one thing about a smaller radar that can move around much easier.
Any more questions? Yeah, so I will send everyone's Dr. Yu's email, so you can also email him.
Okay.
Okay, so let's thank Dr. Yu again.
Thank you.